There we go. So I'm going to ask the awkward usual question is, can anyone see my screen? The most commonly used phrase of 2020, I think.
Yes, we can.
Yeah, we can.
Marvelous. Cool. So thank you for that great introduction. As mentioned, this is the third part of the Android hacking workshop. So I normally run these as like a full day, quite intensive 8-hour workshop, but I try to break them down into small little chunks, at least to get people on the journey of going. And as mentioned, this is the Android hacking 103, so the third and final part of these workshops. And hopefully by this point and leaving the free workshops, you'll have an ability to go ahead and do more things and have more interest in Android hacking apps, hopefully. So I kind of started from like a very beginner point of view. We talked about some of the background around Android, some of the security of Android. Last time we went ahead and installed Droza, and we bypassed the login screen of the mobile banking app. And this time, I'm going to look at reverse engineering and some of the shit that some devs do, not all devs, but as I can see a glare from Jenny as a software developer. So it's not all, I'm saying all devs, but yeah, it's in my experience anyway. And I know it's hard being a dev, right? You have to write like really clean, fast, beautiful, efficient code. And then this security thing, which is like a full-time job for me, can you do that as well? So I don't mean to make fun of devs. It's just easy to do. So I do. Cool. So just going to do a quick recap of hopefully where people are in order to progress. And then if not, the previous 2 sessions are on the latest Hacking Society YouTube channel, and there's a torrent to download in case you're following along and need to go back. But hopefully we're at the point where the virtual machine loads, the Android emulator loads, and we can log into the banking application. And you'll need to boot up the VM, get it loaded, and we'll then need to run the background services. This is the same thing we've done the last couple of times. So making sure that we're running that Python app.py, you get that message saying the server is hosted on port 888. And again, don't close that window because that is going to run the background services for us, and we're going to need that in order to log into the banking application. And then we need to start the emulator. So again, in a new terminal window, run the command emulator at Android 6_86. It takes a little bit of time. So if you are following along, worth doing that now if you've not done so already. And then I'll introduce what we're going to be talking about today. So I don't know how I haven't mentioned this before now, but there is a mobile top 10 that exists. They kind of, for anyone who's unfamiliar with OWASP, it's the Open Web Application Security Project. And the ethos is it's run by people that volunteer their time. The 99% of the content is absolutely free, copyright free, free to reuse, circulate. And we run this thing called the top 10. So it started off with the web application top 10, looking at the 10 most prevalent and common vulnerabilities. It started in around about 2004, 2007. And every 3 years start to get updated. What's going on at the moment, I think they're probably due for a renewal of the mobile top 10 probably next year now. But the idea is that it should try and give both developers and attackers an idea of the most common bugs that are happening at that moment in time, and an idea of things to fix. And they're not necessarily in any particular order. So just because something is number 1 and you've got number 9, it's not necessarily to say you should fix number 1 before you fix number 9. It's just an unordered list of the 10 most common identified vulnerability types of that category. And for mobile, we're going to be looking at 2 this evening: the reverse engineering aspect and the extraneous functionality aspect. So 2 of the mobile application top 10. So reverse engineering, this is one of the reasons why I love Android, because I can take an Android application and I can take it back to its source. So when I'm looking at hacking web applications, normally there's some interaction between my browser and the server. The server does some kind of processing, and then it gives me a response back. And I have to kind of voodoo a little bit about, or make assumptions about what's going on in the server land, what processing it's doing, what information it's taking, and then how it's giving me a response. Whereas I really like, especially Android applications, but also iOS applications, because I can reverse engineer that that application. I can look at the source code, and I don't quite get the comments that developers sometimes put in, but I'll get the methods, and I'll get an understanding of what the application is doing. I can find some hidden methods and functionality. So occasionally I found weird things like API keys to a AWS backend just stored in plain text in an Android application, because the Android application needed to talk to that AWS backend, and what better way than just sticking the AWS key in there. It worked absolutely fine. Sometimes ways to bypass security logic. So I've found things where there's like a true false flag set somewhere in some source code. And if I can reverse engineer, maybe I can see how that flag's been set. Maybe I can bypass some of that logic. And code tampering is not something we're going to look at necessarily this evening, but it's something to look at in the future if you're interested. And what we can do is reverse engineer the application, make changes to it, re-sign it, and then run the application again. So if it's got some protection on, let's say it's a streaming service, and the streaming service won't let you download the actual stream because that's the whole business model. But maybe you can make some changes to the Android application, re-sign it, tamper with that code, rerun it, and there's a high likelihood that that application will run again, and therefore you can bypass some of the security controls. And then the other part we're going to look at this evening, which is linked, is extraneous functionality. So this shouldn't happen, but happens because rush production so often happens when there's a requirement to get something into an Android application or mobile application. When developers or QA testers or analysts are testing this application, they need a quick way to log into the application. So maybe they'll put a shortcut in there that then should be removed once it's made its way into production. But sometimes that doesn't happen. So if you're able to reverse engineer the Android application, you can then look for these shortcuts, these backdoor functionality, and then abuse them as an attacker. And I find that's you don't kind of get that functionality necessarily. You don't really get comments in the code on a website, but you sometimes get this extra information passed into an Android application. And one other thing I want to put in here was Smiley. So Smiley is we're not going to be using it this evening, but I think it's important if you want to take this further. When you reverse engineer the Android applications, we're going to be looking at Java because that's what the Android applications are mainly written in, although Kotlin's kind of what becoming more prevalent now. But when you reverse engineer an Android application, you can convert it to Java and convert it to Smiley. You can make changes in those code bases based in Smiley, and then re-sign the code. So what we're going to do is we're going to take the Android application and we're going to pull it down from the device, and then we're going to reverse engineer it and have a look at some functionality of that. So what you need to do is inside the Android, inside the Droid Andy VM, if you open up a new terminal window and issue the command adb shell pmlist packages -f bank, what this is going to do is, we mentioned ADB before, but ADB is a way that the virtual machine talks to the emulator. So you need to have the emulator booted, you need to have the backend server running, and what this is going to do is PM is package manager, so it's going to list all the packages installed already in the application, and the -f is just a filter. So we know that we're looking for the Android insecure banking application. That's the one we're going to be messing with. We've used this command before because we were particularly interested in the workspace name, which is com.android insecure bank v2. We use that a lot when we're doing the Droid attacks because we needed to know what that package was called. But we're looking for the APK location, and you should get something along the lines of this. When you run this command at the top, you should get this kind of output at the bottom. There's a missing hyphen here, apologies for that. But you get package data app com.android insecure bank v2-1 /base.apk, and that tells us where the APK is downloaded to on the device, and it's that we're gonna pull and mess around with. And I don't know if you remember, but on the very first time you did this workshop, I mentioned that the /data/app folder was readable by anyone. So anyone with any permissions can just connect to the phone with some prerequisites in place and pull these APK files. So what we now need to do is actually get this banking APK so we can then, off the device, get it onto our workspace, onto the emulator, onto the virtual machine rather, and then we can start messing around and having a look at the actual code. And we use this using ADB again, but we use ADB pull. So ADB pull pulls data off the emulator and pulls it into whatever local directory we're running in at the moment. So if you issue the command ADB pull, we know that the base.apk is the location shown above. And we're going to just save it as bank.apk just because it's easier. So if you write all that down as one line, ADB space pull /data/app/com.android insecure bank-1 /base.apk, there's a space there, bank.apk. It'll take a couple of seconds, but that will pull that base.apk down from the emulator, save it into the current working folder as bank.apk. And that's the first kind of process we need to do before we start messing with the banking APK. Just give people a couple of seconds. Cool. So we talked again, as part of the first workshop, that there was several makeups of the Android APK package, and one of the things we talked about was this classes.dex file, and that is where all of the bytecode and all of the compiled code that the developer makes is stored. So that's the interesting part, and that's going to be the thing we look at this evening. And the easiest way to do that is just to pull that classes.dex file using the command. So unzip, because it's just a compressed archive. We talked about that again on the first workshop. So we could rename it to .zip, but there's no need. We can just use the unzip. We pass in the -p bank.apk because that's the file we want to unzip. And all we want is one file from that. So we don't need to extract the full archive. If we just say we want classes.dex, use the angle redirector and output that to classes.dex, that's going to extract that code for us. And we can then look at manipulating that classes.dex file. Again, I give people a couple of seconds and then I'll move on to the next slide. So just to recap, we've pulled the Android APK file from the device, and we've now pulled the classes.dex file out of that APK file. So we've now got some of the bytecode that we need to analyze. So the next thing we need to do, the dex file is no good to us. That's not a format that we can read. So we need to convert that into a Java file. And we use that using a tool called dex2jar. And that's just going to take that classes.dex file and turn it into a jar file that we can read using some of our Java tools. So if you run the command dex2jar space classes.dex, it'll take a few seconds, maybe 10, 20 seconds, and you'll get this output at the bottom saying it's outputting as a file classes-dex2jar.jar. And that means that we can then use Java tools in order to view the actual code that makes up the application. I mentioned Smiley before, so whilst we can view the code in Java, we can't make changes to it in Java. So that's normally why we'll take 2 steps to reverse engineer. We'll reverse engineer it as Java. We'll then view that code, look for vulnerabilities, and then if we want to make changes to it, we'll need to do that in Smiley, which is a very different and horrible, in my opinion, language. It's really difficult to work with. It isn't particularly pleasant and easy to use. So I kind of decode them both and look at them side by side. So once you've run that dex2jar classes.dex, hopefully you'll have a classes-dex2jar file. And then we can just look at the source. So we can use JDGUI. This is the tool which is installed on the virtual machine that has been provided. And if you run JDGUI classes-dex2jar.jar, that will open up the classes.dex file, which we converted into a jar file. And essentially, we're going to get the source code of the application. Now, for this instance, we used the Insecure Bank v2, which is open source. So we could have gone to the actual GitHub. We could have looked through the source code and found vulnerabilities that way. But I think it's important to show that for some applications that are open source, it's not too difficult to be able to pull those applications off. So, you know, where we did the filter -f bank, we could have put WhatsApp in there, Twitter. If those are installed on your device, you can pull those APK files off, reverse engineer it, and then look for vulnerabilities or just look at the code yourself. But yeah, for the purpose of this, we've been focusing on the Android Insecure Banking application. So that's what we're gonna look at. So once we've got the JDGUI, there is a weird backdoor in the application, which is quite uncommon. It's not one necessarily I've seen, but if you look inside on the left-hand side of the window pane, it'll say COM, and if you expand that COM, you'll have Android.InsecureBank v2. If you expand that, you'll have a series of Java classes, and inside that Java class section, you'll have doLogin.class, and that's a class which is called when we are presented with the logon screen that we bypassed earlier last month, in fact, on the second workshop. And if you have a look at that doLogin.class, and if you scroll down towards the bottom of that file, you'll see a lot of code, and it's not super important that we understand all of the code, but you'll probably see something towards the bottom that says doLogon.thisname.username.equals. And I'm not a developer. I can read Java. I don't necessarily can write much Java, but you can see that there's a username hard coded in there. And this is what someone may put in their application because they don't want to type a complex username and password. They don't want to register for a service. Maybe a developer wants to quickly log into the application, do some testing as a test user account that's created on the actual APK, so they don't need to go ahead and create some fake credentials in the database. And this gets delivered to the application. This is quite realistic. I have seen this a couple of times that applications have made it to production. And part of the problem is when the application is deployed on the Play Store, I can download version 1 of that application. If a user downloads, if they then realize what's gone on, they revoke that application and push version 1.1 to the Play Store. Well, I've already got version 1, so I can already see those flaws and vulnerabilities that already exist inside the application. If you've not been able to identify what the username looks like, hopefully you can see the screenshot. I will make it slightly bigger, but there should be a line that says if do login this username equals dev admin, and then I'm not going to pretend to understand Java, but it logs in, right? It some magic happens in Java and it logs me into the Android application. So what I think from this is that, well, that's pretty weird that there's got this kind of weird bypass here. There's a username dev admin. Let's try that inside the Android application. And what sometimes I do is I'll search for the word username, I'll search for the name password, I'll search for API, I'll search for keys, I'll search for a variety of terms that I think, well, be weird for these kind of words to exist inside an Android source code. And maybe sometimes people don't realize that you can fully reverse engineer these applications once they've been delivered. Just to kind of show that a little bit bigger, you can see we've gone to the COM Android.integer bank v2, and then here's all the Java classes, and this is the do logon class. And then along here we've got dev admin. There we go. So if login equals dev admin, then login essentially. It's going to let me log in absolutely fine. So if you open up on the emulator the Android banking application, we do that by going to the application menu, and then once that's there, there's the blue and white integer banking application. If you then, when you're prompted by the logon screen, just type the username dev admin, no password, and click log on, hopefully you'll be presented with this screen where you've got the transfer view statement, change password, and the device not rooted. So essentially, we're bypassing that login screen. You can check that by putting something other than dev admin in, and obviously something other than the Dinesh username password that we've tried before, just to prove that it is doing some verification. You can't just log in with username Andy and the password Andy or anything else. It is specifically this hard-coded username that lets you bypass that login process. And you could go further. You could look for more vulnerabilities. You could pull apart other applications. And I find reverse engineering quite interesting as a technique. So what I'll generally do is I'll use the application as part of a penetration test. I will then pull the APK down. I will reverse engineer it. I'll look for these hard-coded keys, API tokens, username, password, backdoors, development functions, debug functions. I'll then sometimes make changes to the application. I'll re-sign, modify the application, put it back onto the device, see if what I did worked. Again, if that doesn't work, make changes. And it's just a repetitive process of looking at the application, looking for the vulnerabilities, making changes, recoding it, re-signing it, put it back on the device, just rinse, cycle, repeat until eventually either I get somewhere and I've been able to find a vulnerability or the application's coded in a way that it can handle those kind of changes. And yeah, so there's my screen logging in. On this login screen, logging as dev admin, and boom, we're into the Android application. So it was a pretty quick one towards the end of the workshop, but I thought it's pretty fun. It's pretty interesting skill to have to be able to reverse engineer applications. I can't think in web app hacking there's been any kind of applications that I've been able to reverse engineer so well, unless they've been open source. And often I'm able to find vulnerabilities without actually running the application, just by reverse engineering. So if anyone's got any questions, feel free to fire away. Now, drop me an email, drop me a message on Twitter, or I'm also on the LHS Slack as Droid Andy as well. But hopefully you've enjoyed this kind of 3-part workshop, and hopefully it'll lead you into more Android hacking.